Hi, my name is Max Colombara, and today I'm with my peer,
Timothy Wagner.
and we're going to be covering the first unit of the Math Analysis and Approaches SL course. Within this unit, there are a bunch of specific lessons that are covered. The following seven are going to be seen in this presentation: arithmetic and geometric sequences, compound interest, inflation and real value, arithmetic series, geometric series, sigma notation, and the infinite series. Quick disclaimer, the content that we're going to be reviewing today is not enough for you to learn out of it. This is just for the sake of a quick, easy introduction or review before a test. Also, the information that we have extracted is not from a specific textbook, unlike our biology videos where we extract all of our information from the Oxford textbook.
Okay, so the first lesson we're going to be talking about is sequences. Sequences are a list of numbers that follow a pattern, and there's two types of sequences that are seen in analysis and approaches math, which are arithmetic and geometric sequences. Uh, the main difference between these two is that an arithmetic series is adding or subtracting the same difference in each term, while geometric series are multiplying or dividing by the ratio in each term. So, for example, an arithmetic sequence could be 2, 6, 10, 14, 18. And here the difference would be plus 4 since it's increasing by 4 in each term. Then a geometric example is 3, 15, 75, 375, and then 1875. In this example, the ratio would be 5, which means that for each term that you go up, it would multiply 5 times. So to understand the formula better of arithmetic sequences, you need to understand what each term means. A1 is the first term of a sequence, so like in the past slide, 2 would be the first term. N is the number of the term you want, so it can be any number. And an is the variable for the term that you're trying to find, so it could be a5, a20. And d is the difference, which as mentioned before is how much is subtracted and added in each term. Okay, geometric sequences is pretty similar. Um, the only thing that's different in this equation is that instead of there being a difference, there's a ratio that is put to the power of n minus 1, which as you could see in the other past slide, there was also an n minus 1, which is also explained here. N minus 1 is used um, so that, as seen here, it's n minus 1 and then n minus 1. It's included in both types of sequences because a1, or the first term in in the sequence, is already included. A1 is already included. So you don't want to multiply or divide or add and subtract it twice because that would mess up your answer of the nth term.
Now for the second lesson of the first unit, compound interest. These problems are mostly going to be seen in exams or tests with a calculator. So you do need a calculator to approach them. Compound interest is used in long-term loans, banking, and other examples. You should have seen this either in 9 advanced or 10th grade. So this is really just review. Now let's dive into the equations and the part of the equation. A would be the total amount after a certain amount of years, with n being that value. P would be your original value at n equals 0, or when you put down the loan. R would be the rate of interest per annum, and now we're going to talk about what annum exactly is. While N in the equation would be the number of years the money is invested. This equation, obviously, as you can see, would equate and take into consideration compound interest, because you might think 1% over, let's just say, 100 years would total out to be 100%. But after a first 1% or ratio being added, you're not going to be taking that same ratio and applying it to the first term. You're going to be applying it to the second term. And so eventually the growth is going to be an exponential type growth. Let's go into the annum. Annum is just a fancy word for how many times per year the interest is charged. So if it was per semester, it would be 2, trimester 3, per month 12, per week 55, etc. So keep this into consideration when you're going to input it into the equation. In the disclaimer, as we saw, this is just review. So if you want to check out these exercises, here you have one that you can try out, but we're not going to be looking over this. But if you want to solve it on your own, you can. And here's the solution.
The next lesson is inflation and real value. This is just an add-on to 1.2, so it doesn't really require that much attention to it. You will basically use this when a problem asks you to find the real value or to account for inflation inside of a problem. This is because of the concept that with inflation, $1,000 now might not be worth the same in 2 years. So if you want to get a real value of a loan and how much money it's truly worth when the loan is finished, then you would have to use inflation and real value. To solve this, it's a pretty simple process. You need to use your future value, which is also A in different formulas. And then you will structure a formula that looks like this, which is real value times inflation to the power of n. Remember that n is the number of compounding periods, equals the future value. So then divide the future value by the inflation rate, and just to exemplify this so you can understand better, if you were asked to find the real value of 15,000 with a 3% inflation rate after 4 years, this is how you would solve it. It would be real value times 1.03, which is the same as 3% inflation, to the power of 4 is equal to 15,000. Then here it just shows what 1.03 to the power 4 is. Then you would translate this into this side and divide 15,000 by 1.126, and this would give you the real value of $11,905. So the loan after 4 years, the value of $11,000, that is what it would be worth originally. Arithmetic and geometric series. So the concept of arithmetics and geometrics stay pretty similar in series. Arithmetics is still adding and subtracting, and and geometric is still multiplying and dividing. However, in a series, you aren't just finding a specific term, you're finding the sum of all the terms. As long as you follow the formulas that say sum, so for arithmetic it would be series n equals n over 2 parentheses a1, or the first term, plus AN, and then for geometric it would be series N equals the first term parentheses 1 minus the ratio over N divided by 1 minus the ratio. As long as you follow these, it's a pretty similar process, so you should be familiar with it.
For the sixth lesson of the first unit, it's a sigma notation. You might have or might not have seen this in previous courses, but it is just essentially a way of compacting the information that is provided in a series. So it displays this type of notation displays the sum of a series without writing out all the numbers. It's still similar, it's just different formatting, and you may or may not see this in exams or tests or quizzes, but it is still very important to keep in mind because if you end up coming across with this type of notation, you are going to have to properly unravel it to get full points within that question. So let's look over it. So the following terms are used in the notation. The actual symbol is the sum of the series. N would be whatever N equals is where you start summing up the series, right? Number above is up to until what term you should sum the series. And then finally the function shown here as 2n plus 3 is simply how you express each term changing. So the bottom is the start, the right is a function, the top is where you stop, and the whole thing is a sum.
Okay, infinite series. An infinite series is still really similar to a normal series, except that it's usually its key characteristic is having a really small ratio, so it will grow very small and incrementally. This is a visual representation of a convergent infinite series. And as you can see, the formula is very similar to what we just showed you, a sigma notation, except that there isn't an endpoint. You can use the same concept as sigma notation since it's a similar concept. There are two types of infinite series: convergent infinite series, which is the ones that you can usually solve and will be shown, which as shown here, it's, for example, 1/2 plus 1/4 plus 1/8 plus 1/16. All of these sum together get close to 1 and they will continue to go forever, but they will never quite reach 1. So it's converging towards 1. Then there's a divergent infinite series, which they don't really have a direction. They're simply growing into infinity or negative infinity, and they don't reach a specific value, so you won't usually be asked to find this, but it's still important to mention.
Thank you for watching. I hope that you guys were able to get your review or introduction out of these few pieces. As always, you should check our other videos. We also cover biology and econ, and the same methodology is used where we introduce or review concepts as a course goes forward. This was IB Simplified 101 by candidates for candidates. Thank you.